Hi, I'm Laren. This is Knife Still Nerds. Today we are talking salt pots and what you can do with them. Are these the secret to stellar properties? Can we heat the steel up really fast in these salt pots and give us awesome toughness and hardness? Let's find out. Okay, first, what are salt pots, also called salt baths? This is a heat treating technique that uses molten salts. So you use a special kind of salt, it melts, and then you've got this hot liquid that you can stick the steel into. For these experiments, I used Neutral Salt B by Hubbard Hall. I got it from High Temp Tools. They sell salt in relatively small amounts, so it's easy to buy. They list the working range as 1300 to 1700 Fahrenheit, but it also says that you should avoid using 1700 for more than short periods of time. In the past, I've also used low temperature salts for os tempering, which is a totally different thing than what we're going to talk about today. I have an article on that. I've never done a video about it. If you want me to do a video on os tempering for bainite, let me know in the comments. Oh, the furnace I used was the Even Heat Salt Bath 709. That holds a 9-inch long pot with some extra that sticks out. They also have them in bigger sizes. I only need to do relatively small coupons, not big long knives, so I only needed the small version. Though when you operate the furnace, first you heat to your target temperature using the thermocouple inside the furnace itself. Then, once the salt melts, you switch over to the secondary thermocouple, you stick it into the molten salt, and then you change the mode so that it's running off of the salt bath thermocouple instead. So that's how you operate it. It's not that complicated, though we should probably talk about salt pot safety for a second. If you've ever heard about heat treating in salt pots, you've probably heard about how dangerous they can be. So if you drop significant amounts of water into a salt bath, it can explode. And you would be in a lot of danger if that happened. You know, it's molten hot salt up to, 1500, 1600 degrees Fahrenheit. And that'll make a big mess, and you want to avoid all those things. So you need to take it very seriously, wearing protective equipment like a face shield and long sleeves, maybe even like a leather apron. But I have heard some knife makers exaggerate the danger also. Like one person was telling me, you got to make sure there are no Sharpie markings at all on the steel, and that could lead to an explosion. I don't think you need to worry about that. So, don't take it lightly. You need to take it very seriously. Make sure you're not getting any water or anything into the pot. Make sure your knives are clean before they go in there. But if you follow the proper procedures and take safety precautions, you should be okay. But you probably want to know why use a salt pot at all. Well, they do have a few advantages. One is that you don't need to protect the steel from oxygen. When you stick the steel in a molten salt, there's no atmosphere. It's just in molten salt. So there's no oxygen to form any scale on the steel or to lead to decarburization. You don't need any coatings or any foil. You can just stick the steel directly into the molten salt and then pull it out and quench. So very easy, very convenient. Another big thing is the rapid heat transfer. So liquid is much better at transferring heat than air. This is why it's extremely scary sticking your hand into boiling water at 212 degrees Fahrenheit, 100 Celsius. That is way scarier than sticking your hand into an oven, that's in air, even at much higher temperatures. You stick your hand into a 500-degree oven all the time for short periods of time so that you can put things in and take things out when you're cooking them, and that's not scary at all because air does not transfer heat as rapidly. So with salt pots, you can heat up the steel very fast. So first, I wanted to measure how much faster can you heat up the steel in the salt bath as opposed to a conventional furnace in air. So I used coupons of 1084 steel that are about 1/8 inch by 1.5 inch by 2 1/4 inch or so. And I used a series of coupons and sticking them in 1 minute increments. So I did one for 1 minute, one for 2 minutes, one for 3 minutes, etc. And then I measured the hardness after quenching in Parks 50. I compared that with a furnace in air. Unfortunately, I was a little bit late with the 2-minute coupon. It was more like 2 minutes and 20 seconds. But by 2 minutes and 20 seconds, the 1084 was 65 Rockwell or so. So basically fully hardened, which means we had to have heated up close to the 1475 Fahrenheit that I had the salt bath set to. With 1 minute, it was still 12 Rockwell, so not heated up, and when I pulled it out to quench it, I could tell it was not the same temperature as the salt. So somewhere around 2 minutes or so, it was heated up. When I did the same thing with air, even after 3 minutes, it was still 7 Rockwell. It had not heated up sufficiently. After 4 minutes, it was 61 Rockwell, so almost there, but not quite hot enough. At about 5 minutes, Then we were at about the same temperature as the salt. And then at 6 and 7 minutes, we peaked out at 66 Rockwell, which is about as hard as the steel is going to get. Now, the required time in the furnace is not just to heat up the steel, it's also to dissolve the carbides. So the steel gets a temperature, and then we hold it there longer to dissolve carbide, to put carbon in solution, and then the hardness is related to how much carbon we had in solution prior to quenching. And at different temperatures, this will take different amounts of time. So I was using 1475 Fahrenheit, and at that temperature, especially with 1084, dissolving the carbides is pretty fast. But at lower temperatures, like there are these cool micrographs from an old study that was done where they use 730 Celsius, 1346 Fahrenheit. And at that temperature, the soak time, so it's already heated to 1350 Fahrenheit, and they hold it for different periods of time. It took 5 minutes to fully transform the steel from the ferrite to austenite. At that point, there are still carbides left, but it's finally austenite, so that when they quench it, it's the dark martensite that they look at under the microscope. And then it needed another several minutes to be able to dissolve most of the carbide. So 10 minutes were required to dissolve most of the carbide after the 5 minutes was already done. So again, some knife makers forget that we're not just heating up the steel, we are waiting for certain things to happen. But we were able to see the difference in this case between the air furnace and the salt furnace, the salt several minutes faster to heat up the steel. Now, to illustrate what I mean with the difference between heating to the temperature versus soaking to get the carbides to dissolve, I did another experiment with 52100. So similar to my 1084 study, I used the same size coupons. 52100 has 1.5% chromium in it, which significantly slows down the time for the carbides to dissolve. I used 1525 Fahrenheit, 830 Celsius with this steel because its optimum austenitizing temperature is somewhat higher than 1084, which only has carbon, manganese, and silicon. So with the 52100, with the same 3-minute hold as 1084 that had nearly 66 Rockwell, with the 52100 it was still only 59. And then that increased up to 7-minute hold where it was a little over 62, and then it basically leveled off, and the further increases in hardness were much slower at that point. And this is why I usually don't recommend trying to do soak times that are as short as possible. I prefer to use a longer soak time to ensure that we are in this region where the steel has leveled off, where we're not seeing big changes in hardness with small changes in soak time. So I see lots of knife makers say that they only use 5 minutes, and with a steel like 52100, that gets you in this sharp transition range, where with a thick piece of steel, you're going to be significantly softer than you are with a thin piece of steel. And so different sizes of knives or different conditions are going to result in highly variable heat treatments and highly variable properties at the end. So sometimes knife makers say that I soak way too long, like 10 to 30 minutes for different steels and austenitizing temperatures. That's not that long. If you're using the right temperature, you don't need to worry too much about grain growth. Even holding for an hour, the grain size isn't going to be significantly larger than a 10 or 20 minute hold. Temperature is more important than time. So it's important that you soak long enough where you are getting into a consistent range of hardness, even with different size pieces. Now, of course, you can soak a little longer if you have larger pieces as well, but ensure that you've soaked long enough. That is more important than trying to shorten your soak time to try to get finer grain size. I will note that this experiment with 52100 and the 1084 was with factory annealed steel, which has a relatively coarse spheroidized structure. And with the relatively coarse structure, it takes a longer soak time. If you use a perlite starting structure instead, it is much less sensitive to soaking time. Now, this isn't always a good thing, but I have recommended this in specific cases such as heat treating in a forge where you don't have good control over the temperature. For a lot of cases, I actually prefer a spheroidized structure, maybe a little finer than what you get with a factory annealed condition, but with a spheroidized structure, you can control your final hardness and your final properties, whereas with a perlite structure or a martensite starting structure, you can't really control things. It just immediately dissolves everything and you get the same properties. So, but I wanted to point out that in certain cases, it is less sensitive to the soak time. Okay, But the real question is, can we get improved toughness with the rapid heating and short soak times that we can do in a salt pot? For this experiment, I used 1084, and I did a 3-minute hold at the 1475 before quenching in Parks 50 and tempering at 400 degrees. I compared that with a normal heat treatment in my conventional furnace in air for 10 minutes with a true 10-minute soak time at the same temperature of 1475. And then I did another experiment in the salt pot where I put it in for 3 minutes at 1475 and quenched, and then I did that 2 more times for a triple quench, followed by the 400 degree temper. So, in this case, the salt pot heat treatment for 3 minutes, I got a little bit lower hardness, about 1 Rockwell C lower hardness than the normal furnace temperature at about the same toughness. So no improvement in toughness and slightly lower hardness. Though nothing to get excited about if there was an improvement in the grain size that didn't show up in toughness. Maybe there was a little more carbide left in the steel with the short soak time, so maybe there can be some advantage to that, but no major improvement in properties in terms of the hardness-toughness balance. The normal furnace did better. Somewhat surprising was that the salt pot heat treatment triple quench did much, much worse for toughness. The hardness was a little bit higher, but the toughness much lower. And, this was pretty surprising. So I looked at the micrographs of the steel, and as expected, the triple quench that went in 3 times at 1475, it had much less carbide. So I think what happened is that we ended up with excess carbon in solution. That can lead to plate martensite and other factors that lead to reduced toughness, because this toughness with the triple quench was much closer to a high carbon steel like 1095 or 01. Those steels in the past I have seen relatively low toughness values because of their extra carbon in solution. Normally that's not an issue with 1084, but with the triple quench, you quench one time and now you have martensite. And when you start with martensite, the heat treatment response is much faster, just like we were talking about perlite versus spheroidized carbide earlier. Martensite is the fastest starting structure to heat treat from. And so it looks like it's actually more carbide is being dissolved than just holding for a straight 9 minutes by starting over with martensite and doing that twice. So the triple quench in this case, we ended up with excess carbon in solution, and the toughness went down significantly. Another thing to note is that the fracture grain was still very fine. The grain size was not affected by the triple quench, at least not in a negative way. Still very fine grain size, it's just the carbon in solution that led to the poorer toughness. In terms of soak time, again, like I was mentioning earlier, I don't like to use very short soak times. Many knife makers say that I soak too long, and I disagree. We did a set of experiments with 8670 a couple years ago, and we did 5-minute hold, 10-minute hold, and 15-minute hold. Well, the 5-minute hold had worse toughness and lower hardness than a 10-minute hold or a 15-minute hold. The 10 and 15-minute holds had about the same properties. We did not have worse toughness or anything by using the 15-minute hold. So don't be afraid of holding the steel for a few minutes longer than is strictly necessary. Trying to go shorter for improved properties is unlikely to lead to a better result. Now, since we had excess carbon in solution with the 1084, the question is, could we have better toughness by using a lower austenitizing temperature to ensure we don't get too much carbon in solution? The answer to that is maybe. With 01 in the past, I was mentioning 01 and can end up with lower toughness because it has excess carbon in solution. I did an experiment where I austenitized lower than normal, 1425 Fahrenheit instead of 1475, and also compared with 1550. And using 1425 led to less carbon in solution and higher toughness. 1550, more carbon in solution and worse toughness. So there is some limit to how low you can go before you're not going to transform to austenite. But could we get improved toughness with the 1084 by soaking lower in combination with the triple quench? Maybe. I haven't tried it. But I do want to still show this result, that a triple quench ended up with worse properties. And I think this is kind of a warning to knife makers. Many knife makers think like, oh, I'll do this super special heat treatment, And there's a good chance, or maybe only a small chance, that I'll improve the properties, but it's not going to hurt it. And my answer to that is oftentimes it does hurt the properties. So using a more conventional heat treatment is often safer unless you have solid experiments that demonstrate that it's actually improved. And I would not have necessarily expected this result of the lower toughness from the triple quench, but then I tested it and found out that it was worse. And so you need experiments to actually see if you're making an improvement. And when you're getting extra fancy with your heat treatment, you're sometimes in danger. We actually did another triple quench experiment with CruForgeV back in 2018. In this case, we used a conventional furnace, not a salt pot. So with CruForgeV, we did 10 minutes at 1450, then we did that a second time, and then we did the final from 1500. With this experiment, we also saw an increase in hardness and a drop in toughness through the triple quenching. But the drop in toughness was not as extreme in this case. I think that is likely due to two factors. One, the chromium addition in CruForgeV does change things, just like we were talking about with 5200 earlier. So its carbides dissolve more slowly, and it is not as sensitive to overheating and getting excess carbon in solution. And number two, we used a lower temperature for the first two quenches, so maybe that was not as detrimental as doing everything at 1475. But I wanted to bring this up because it is another case of triple quenching where we didn't necessarily see an improvement. And also, when we did this experiment, one of our concerns was, oh, well, maybe it's because we soaked too long, and that's why we didn't see a decrease in grain size and an improvement in toughness. But now we've done it with a salt pot with 1084, and even with much shorter soak times, we did not see an improvement in toughness with a triple quench. So maybe there are certain cases where we can improve properties with a triple quench, but this experiment and the prior experiment with CruForgeV did not demonstrate that. Another prior experiment that is related to what we're talking about here is from Dr. John Verhoeven in his book Steel Metallurgy for the Non-Metallurgist. He wrote that for knife makers and bladesmiths several years back. And he also did a triple quench experiment with salt baths. He did it with 1045, 1086, and 5150 low alloy steels. The first thing he did is he heated the steels to 1650 Fahrenheit for 15 minutes and quenched. Then he measured the grain size. Then he heated each steel to 1450 for 4 minutes each in a salt pot. And he quenched, and he did that 3 times. And then he measured the grain size again. And he found a significant decrease in grain size by doing the 1450 triple quench. And that 4-minute soak time is just 1 minute longer than what I did at 1475 for 3 minutes with the 1084. So why did he see an improvement and I did not in my experiment? Well, I think it makes sense given that he first started with 1650 for 15 minutes in quenching. 1650 is definitely hot enough to significantly increase the grain size in these types of material. And then when you repeat the heat treatment from 1450, then of course you can refine the grain size. I would be interested to see how fine you get the grain size by only 1 or 2 cycles rather than all 3. Or maybe you could just anneal the steel and then heat treat it from 1450 and get the same grain size. Those would all be interesting experiments. But you can't look at his experiment just on its face and say, oh, a triple quench leads to finer grain size, because it's starting from a larger grain size to begin with and seeing if lower temperature cycling can decrease the grain size. And of course it can. And the other important point is that I was measuring toughness while he was measuring grain size. It could be that I got the grain size a little bit smaller, but going from a very fine grain size to a slightly finer grain size does not guarantee an improvement in toughness, which is what I was measuring. So after all this, do I recommend salt pots for austenitizing? With the way that I work, I don't really think salt pots are for me. The main reason being that I heat treat a wide range of steels with a wide range of austenitizing temperatures. So if you only use a narrow range of steels with a narrow range of austenitizing temperatures, you may benefit from salt pots that you can work a little more quickly and heat treat a lot of small pieces rapidly. But if you're outside of this range of the neutral salt B, 1300 to 1700, like you need to heat treat a stainless or a high-speed steel from a higher temperature, you need to get a different salt. And so you would need multiple pots with different salt types in them to be able to work in the right range. And that is a little bit more than I want to handle. But, I am doing experiments on lots of different steels. I am not a knife maker, and so my needs are a little bit different. Now, not having to use coatings or foil, that is nice, but it is not enough to switch me to the salt pots. Of course, there are some safety concerns, and you have to maintain the salt and all of that. So for me, I probably won't be switching to salt pots for austenitizing most of the time, but for certain knife makers, maybe this is something you would be interested in. So to summarize, salt bath furnaces, they have much faster heating rates so that you can spend less time heat treating. There are potential advantages to heat treating faster, but I did not see any. Using short soak times, rapid heating did not lead to an improvement in toughness. And somewhat surprisingly, using a triple quench led to a great decrease in toughness. Perhaps the grain size was finer, maybe it wasn't, but the main overriding factor was that we got extra carbon in solution, and that dropped our toughness. So I did not see any benefits to either a triple quench or rapid austenitizing in this case. Maybe there are specific scenarios that could be created where there would be an improvement in properties, but with these experiments, they did not show up. So salt pots, they are very cool, they're very interesting. You need to be careful when you use them. And let me know in the comments if you have found any good uses for salt pots in the way that you work. So thank you to all my Patreon supporters, again, to be able to do things like buy a salt pot furnace or buy salts or buy steel for doing these experiments and all the time it takes. I paid for metallography for this. All of that money comes from Patreon. Your Patreon dollars go towards experiments like this one. So if you want me to keep doing more experiments, please become a supporter on Patreon. If not, that's cool too. Subscribe and like and all of those things. So I hope you enjoyed this salt pot heat treating study. Thank you. Bye-bye.